All right, let's talk about solving logarithmic equations. Okay, how do we solve a logarithmic equation? Now, before we get into this, you got to be really careful about how you solve these. The key that you got to keep in mind, there's some restrictions on these numbers in the logarithm. A and m, the base of the logarithm a, and then that value inside the logarithm m, both have to be positive, and a can't be 1. And I'll tell you why that's important here in just a minute as we're solving these equations. But just know right off the bat, as we're solving equations like these, there are some restrictions on those values there. All right, so how do we solve this? 5a, log base 3 of 4x minus 7 equals 2. This looks really challenging when you first kind of approach it, but what we can do to make this a little bit easier, this is one technique to solve a logarithmic equation, is to rewrite it. We can rewrite this as a base 3 squared equals 4x minus 7. So we rewrite it as an exponential expression. All of a sudden, if we square that 3, this thing doesn't look nearly as challenging, right? If we add 7 to both sides and then divide by 4, we get that x is 4. So it turned out to be a really simple equation to solve. So that's one technique, rewrite it as an exponential. Okay, and just to check this, if we do log base 3 of 4 times 4 minus 7, we get log base 3 of 16 minus 7. And then log base 3 of 9 equals 2, which is true, right? 3 to the second power is 9. So that does work out. We can check that and see that it doesn't violate anything. We don't end up with a negative value here. This value is positive, so it's all good. 5b, log base x of 64 equals 2. Again, it looks a little daunting to start out, but if we rewrite this as an exponential, we get x squared equals 64. All of a sudden, that's not too bad. We can solve this a couple of ways. One way, we could consider it to be a quadratic, set it equal to 0. So we could say x squared minus 64 equals 0. Factor it as a difference of squares. And say, what are the zeros here, right? The zeros of those two factors. We could get negative 8 and positive 8. Alright, so we get two solutions here for our values. Now, the question is, do both of those work? Does it make sense to say log base negative 8 of 64 equals 2 and log base positive 8 of 64 equals 2? Are those okay? Well, this one's fine. This one, on the other hand, has issues, right? This number right here can't be negative. So that means that negative 8 is actually not a solution, and only positive 8 works. And so that's one of those restrictions we mentioned earlier. The base has to be positive, and it can't be 1. So we toss out negative 8, and we're just left with positive 8 as our solution. All right, e to the 2x equals 5. Now here, we've got, this is actually kind of it's an exponential equation, right? E to the 2x equals 5. And the problem here, if you think back to the last section, to solve an exponential equation, the technique we would have is to rewrite both sides as powers of the same base, right? So e to the 2x equals e to what power? So e to what power is 5? That's a hard question to answer, right? Because e is an irrational number. It's 2.718. It goes on and on. And so there's not really a nice, neat way to rewrite this as powers of the same base. You run into the same problem trying to rewrite e as a power of 5. So we can't use that technique that we had in the last section. It just doesn't work. So what we can do instead is we can say, all right, e to the 2x equals 5. What if I rewrite this as a logarithm? So it's a natural log. I remember we could say log base e, but that's the same as a natural logarithm, right? So we're going to say natural logarithm of 5 equals 2x. So, all right, natural logarithm of 5 equals 2x. Can we solve that for x? Sure, we can divide by 2, right? And say that natural log of 5 over 2 equals x. And that's solved, right? We solved it for x. Now this doesn't appear to be a number, natural log 5 over 2, but if we go to the calculator and say what is natural log of 5 and then divide it by 2, we get 0.804 or 0.805. So that's a number, right? So even though this looks weird because it has the natural logarithm in it, just know that that is a number. Okay, natural log 5 is a value, and we can plug that in the calculator and get an actual number for it. So we have solved that. Okay, what if you wanted to check that? Could you say maybe what's e raised to the natural log of, what was it, 5 over 2? And get oh wait, that's x, so we actually need to multiply it by 2, right? So let me back up. And we're saying e to the natural log (5 over 2). We actually need to multiply that by 2. Let me back up one more time. So e raised to the 2 times x power, and we get a 5. Hey, that checks out, right? Should equal 5. So you can check these on the calculator. It's a little tricky to do to make sure you get it typed in right, but it can be done. All right, example 6 says the blood alcohol concentration, BAC, is the amount of alcohol in a person's bloodstream. So the BAC of 0.04% means a person has 4 parts of alcohol per 10,000 parts of blood in the body. I think that's a concept we're all familiar with. A relative risk is defined as the likelihood of one event occurring divided by the likelihood of a second event occurring. So for example, say if someone with a blood alcohol concentration of 0.02% is 1.4 times as likely to have a car accident than an individual who's not been drinking, we'd say the relative risk of an accident with a blood alcohol concentration of 0.02% is 1.4. Okay. Relative risk, the likelihood of the person who is drunk being in an accident divided by the likelihood of the person who is sober. Okay. 1.4 divided by 1 gives a relative risk of 1.4. Okay, so that's just setting up some concepts for the next question, and that is this. Recent medical research suggests that the relative risk R of having an accident while driving a car can be modeled by this equation. R equals e to the kx, where x is the percent concentration of alcohol in the bloodstream and k is a constant. And so that's what we got. There's an exponential function, r equals e to the kx. R is the relative risk we just talked about, x is the blood alcohol concentration, and k is the constant. Okay. So part A, let's kind of jump in here and see what we're even doing with all this. Medical research indicates that the relative risk of a person having an accident with a BAC of 0.02% is 1.4. Find the constant k in the equation. And so if we plug in these numbers. The relative risk is 1.4. Blood alcohol concentration is 0.02%. And we don't know the value of K. So we plug in the numbers we know and we get this equation. It says to find the constant K, what's the value of K? So that looks like an equation we just solved, right? We can rewrite this as natural log of 1.4 equals 0.02 K, and then divide by 0.02, and this natural log 1.4 over 0.02 is K, which we can punch into the calculator. Natural log natural log of 1.4 divided by 0.02, 16.82. So we got that K. Part B. Okay, using that value of K, what's the relative risk if the concentration is 0.17? So in other words, what's the relative risk R using 16.82 for K times 0.17? So notice how we just plugged in K and X, trying to figure out what R is. Now we would expect R to be higher, right? The risk is going to be higher because this person has had more to drink. So we just need to know what this value is. E to the 16.82 times 0.17, we get 17.45. All of a sudden that person is 17.5 times as likely to have an accident. Okay, makes sense. Said it would be higher. Okay, using the same value of K, what BAC corresponds to a relative risk of 100? So now we're saying, all right, R is going to be 100. And we're trying to find the blood alcohol concentration, right? So E to the K is 16.82 X. We're solving for X now, the blood alcohol concentration. Well, again, that looks just like a problem we just worked. We could say natural log of 100 equals 16.82 X. Just rewrite it as a logarithm. Divide by 16.82. And whatever natural log of 100 divided by 16.82 is, we get 0.274 or 0.27. So that's blood alcohol concentration of 0.27. Alright, so this is all great. You know, we've got this nice little function that lets us figure out, you know, how likely you are to have an accident depending on how drunk you are, but there is a usefulness to this, and it, you know, one thing you could do with this sort of model is talk about laws. You know, you could, instead of trying to determine how drunk is too drunk just based off of, you know, well, some blood alcohol concentration number that, you know, doesn't necessarily maybe tie directly to some sort of meaning while driving. You know, this model lets us relate a blood alcohol concentration to a relative risk, right? And so we could say maybe that that we want to know, all right, if sometime, you know, if the law says that someone with a relative risk of 5 or more should not have driving privileges, when should they be arrested and charged with a DUI? So we're saying that, you know, if you're 5 times as likely to have an accident, you're too drunk to be driving. And so we want to know what blood alcohol concentration that corresponds to. And so we don't know the blood alcohol concentration. We know the relative risk is 5, using that same value for K. We can rewrite this as a logarithm. Divide by 16.82. And then whatever natural log 5 divided by 16.82 is our answer. I'm just going to reuse this last calculation I did. Change the 100 to a 5 and we get 0.096. So that would be the legal limit if we were to draw the line at a relative risk of 5. Okay. And I believe that's pretty much it for this section. So if you have any questions, please let me know.